Thanks for joining me. It is Tuesday. It's 3 o'clock. That means it's Tech Tuesday. And today's topic is quantum networking. Be right back. Today is Tech Tuesday, and I was going to be talking about quantum networking. I saw this article, and I didn't realize that we had come this far with quantum computing and quantum networking. So I wanted to talk about this article, and then I wanted to basically show you or talk a little bit about quantum mechanics and some of the things that make this possible. So it's going to get a little bit deep, but I can only go so deep. So hopefully that'll make sense to you as what I'm talking about here. So let's first read through this article. Hang on one second. Phone is ringing, but it's not anybody I need to talk to. So here we go. So momentum for cutting-edge quantum networks is building. In New York City, quantum technology developer QNect has built a quantum network testbed and recently announced an expansion of that network. In contrast with traditional fiber optic communications, which use light pulses to transmit information in the form of ones and zeros, a quantum network uses entangled light particles, which have the potential to carry more complex data. It's complex technology that offers potential security as well as capacity advantages. So I'm going to explain a little bit about quantum entanglement here in a minute, but I wanted to read through this article just to kind of set the stage for that. Also, we'll talk about security as well. The QNect network, known as Gotham IQ, is being expanded to connect the Brooklyn Navy Yards to New York University. QNect is partnering with the Center for Quantum Information Physics at the university on the project. The network eventually is expected to be available to the financial services, critical infrastructure, and telecom industries. The news comes several weeks after Tennessee utility company EPB announced that it was building a quantum network in Chattanooga. EPB is the same company that made headlines a decade ago when it built a gigabit network in Chattanooga. So EPB, before anybody was talking about municipal broadband, or maybe people were thinking about it, I guess, or talking about it, but they came out and they built a fiber network for the city of Chattanooga years and years ago. QNect Quantum Network, in a press release, QNect said that connecting its testbed to NYU will enable the company to showcase protocols and technologies that will eventually be used by a wide cross-section of customers and partners within the Manhattan borough and across New York City. QNect Chief Science Officer Dr. Mehdi Namazi said the company's quantum network is a first critical step towards QNect providing entanglement as a service. I love that, entanglement as a service. Quantum protocols that will allow our customers to have access to verified, fully secure, entangled particles between their internal nodes and the option to freely expand their entanglement nodes with other partners in the city. Again, I'll talk about entanglement here in a minute. In the coming months, he said, we'll be pleased to provide data insights from this milestone, specifically tied to polarization stabilization. I'll mention polarization as well. QNect says that its first generation of Metropolitan Products Suite will be completed during the middle of the year and will provide scalability and the capability of being deployed in crowded urban environments. The technology also will be operational at room temperatures, unlike the fragile climate-controlled laboratory settings that labs use. So right now, like a lot of things, they have to keep things very, very cold to keep things stable. So it sounds like you won't need this big refrigerator truck of equipment to be able to do this. Namazi said that the testbed will showcase protocols and technologies that eventually will be available. Notice eventually will be available, so we're not there yet. CQIP and QNect, along with Sandbox AQ, will develop a quantum information science curriculum and dedicated lab that they hope to help create a quantum workforce in New York City. Let me close that. In 2021, QNect said it commercialized quantum memory. That memory is the heart of QNect's Quantum Repeater product suite, which provides long-distance distribution of entanglement across existing telecommunications infrastructure. So one of the challenges now, again, before I get into a lot of the technology here that underlies this, but one of the challenges with quantum computing and quantum networking, especially quantum networking, would be distance. That you can't go very far because there's a lot that can interfere with this entanglement that we're going to talk about here. So they would need repeaters to do this, and looks like they're developing that as well. So anyway, I thought this was an interesting article here in Telecompetitor, talking about the future. It doesn't go into a lot of details about what it all means. So I was going to try to explain a couple of the things that make quantum computing and quantum networking work, to just kind of for a layperson like myself. So And I found this that I thought was a really good way of explaining it. So when you get down, of course, Einstein described the world, the macro world that we lived in, with his theory of relativity and E equals mc squared. So he really described the way things work at the level that we can see, gravity basically. But as you get down to the quantum level, things get really weird, really fast. So some of these things sound incredible and hard to believe, but this is kind of the way that things operate in the quantum world. So this is the idea of superpositioning, and then also entanglement, and the way those things work. So superpositioning is where you don't know the state of a particle until you actually observe it. But before you observe it, it can be in multiple states. It can be in two different states. So, for example, a photon could be polarized in one direction or another. It could be vertically polarized or horizontally polarized or diagonally polarized. And there's different probabilities, I guess. Probabilities that it could be one or the other, but you don't know what it is. It doesn't really take, really what it is, it doesn't take the state until you observe it. So it could be in either state until you look at it. So here's an example where you've got two balls and you've got, let's say you have two entangled balls, each in its own box. In this metaphor, the balls can be either yellow or red once observed, but for now they're in a state of superposition, or both yellow and red at the same time. So you've got two particles, let's say two photons, and again, this could be polarization instead of colors, but you've got these two particles, and until you observe them, they could be in either state of, in this case, let's say red or yellow, which is kind of crazy. And that's the entanglement part. When you've got two particles that were previously together in a system, like maybe two electrons in a atom or two photons that are generated in a way that they are entangled, then they remain entangled. And it doesn't matter how far apart they are. So you could have them 10 feet apart, 10 miles apart. You could have them across the country. You could have them across the universe. And those two particles are entangled. And they both would be, in this case, let's say, in a case of having both yellow and red. But then as soon as one person observes this, it says, until you observe the balls, and then we have one observer says, hey, mine is yellow. If the first one is yellow, the other one says, hey, mine is yellow too. So as soon as one person observes the ball, then the other one is the same exact state. And then same thing if it was red. If the first person saw that it was red, then the other person would say, wow, mine is red also. So the objects remain connected even over vast distances. Scientists think of entangled objects as really being a single object. So that's really what they're saying, is it's not like you've got these two separate photons that are really far apart. They look at them as one single connected object. And then what else do we have here? So, but what if one observer decides to look at their ball from a different angle or side of the box? The balls would revert back to a state of superposition and have a 50% chance of being yellow and 50% chance of being red. Now, that's her looking at it from a different angle. The viewer might find a yellow ball now, even though the pair of balls had previously both been red. She's like, what the heck? This ball was just red. Now, he's still looking at it from the other position, and it's still red. Hers is yellow. Now, if the second observer also looks at their ball from the side view, it will match what the first observer saw. The balls are still entangled, but what the viewer sees depends on how they look at the ball. This is because the entangled information about color does not lie within one ball, but exists in the connection between the balls. So again, these are like one object. So this is something that Albert Einstein, he didn't like quantum mechanics because it totally blew up his idea of what the world should look like. So in fact, he called something like this spooky things at a distance, something like that. So, he was not in favor of quantum mechanics. He didn't think it was really anything that really made sense. He thought there had to be some other underlying principle. And he thought actually that when we were seeing these things, that there were actually some properties within these particles that were making them that way. But there have been experiments since then that have determined, no, it really is this way, that there's this indeterminate state until you actually observe one of these particles. So when they're talking about entanglement and these networks and supercomputing networks, they're going to take advantage of the fact that you can have these kinds of particles be in a superimposed state, which means that you can have multiple kinds of parameters. Normally in a computing system, you have bits. You've got a bit of a 1 or a 0, so something's either on or off. Well, in quantum computing and quantum networks, you've got something called qubits, where they're not on or they're not a 0 or 1. They're really a 0 and 1 at the same time. They can be 1 or 0 at the same time, and they're not a 1 or a 0 until they're observed, in a sense. So that's, again, a little bit weird and spooky. Now, the other thing that Einstein didn't like, he said he didn't think God played dice with the universe. So there was a scientist named Schrodinger. You may have heard of Schrodinger's cat, and he tried to take this quantum weirdness that's going on and apply it to kind of the macro world that we lived in. And he had Schrodinger's cat, which was kind of a thought experiment to say, well, what would this look like, and how weird would it be if we tried to make this apply to our real world? So his experiment, basically what he had here was a box that he put a cat in, and in that box he also had a radioactive element that was decaying, and he had a sensor like a Geiger counter, and that counter then was connected to a hammer, and in that box also was a vial of hydrochloric acid, I think. So the idea is that in an hour, there's a 50% chance that that particular radioactive element would decay, sending off this atom that would then be counted by this Geiger counter. And that Geiger counter, if it saw that, would then drop the hammer, it would break the vial, and it would kill the cat. So in that hour, basically, there's a 50% chance that that cat could be alive or dead. But according to quantum mechanics, because we don't really know until an observer checks this and sees whether that atom decayed or not, then that cat could be both alive and dead at the same time. That's the really weird part. So the cat could be alive, in a state of being alive or dead at the same time. Now, when you open the box, it's either alive or dead. But before you open the box, it's in a state of being both alive and dead. So that is one of those weird things that I can't explain, and nobody else can, exactly whether that's really the case. But this was Schrodinger's way of saying, this doesn't make any sense. But again, scientists today are using these things to create these quantum computing kinds of things. So they're using this superposition stuff and this, as you can see, quantum entanglement, where you've got these particular particles like photons. That's basically what they're doing, is they're using polarization. So they've got photons that could be either polarized in one direction or another. So what this is going to allow, again, having these multiple kind of properties for these qubits, is that you can have much, much more powerful computers. I mean, really an order of magnitude powerful. So this is a totally different computing system. And then on the communication side, you can use these quantum networks to communicate. So it's going to take new materials. They're creating new materials. They're taking, instead of just silicon, which can only go so far, they're taking, something like graphene, which is like a one atomic layer material that they then can etch or kind of make little ripples in to be able to use as chips. So you're still going to need chips. And then instead of bits, you've got qubits, and then you're still transmitting data, but it's all on this quantum level. Now, one of the reasons that this can improve security, and you might think, well, this will make security bad, because now you've got, I think it's called RSA security, where if you go to a website, for example, and you see the little lock on the website, let's say you're buying something on Amazon, and you see the lock up there, when you type in your credit card and you hit send, that information is encrypted through a public and private key, sent to Amazon, and then nobody along the way can read that information. It would take a lot of computing power in order for somebody to be able to take that information and try to somehow recreate what it was. So there's a public key that anybody can use, and then the private key that the receiver has unlocks that. And somebody along the way cannot unencrypt that unless they throw a whole lot of computing power at it. So it's just not anything right today that can be done. But if you had a quantum computer, then these kinds of encryption technologies that we use today could be easily broken, because you've got a magnitude more computing power to be able to do this. So, will this have a problem with security? Well, in actuality, quantum computing can actually improve security, because you can use the quantum entanglement and some of the features of that to prevent somebody from actually reading the message. And the way that would work would be through this superposition and this entanglement. So you could have encryption in such a way that you've got these two entangled particles, and as you're transmitting this data, as we saw, if you observe the data, then you actually change the entanglement. You can mess up the entanglement. So if you're communicating that data and it's quantumly entangled, then if somebody reads that information along the way, then the receiver will know that that information has been changed, and they can then not take action and request another set of data. So it actually improves the encryption and the security using that. So that's going to be an interesting feature as well. So I think it's going to be very interesting to see where this progresses in the next 5 or 10 years. They are already, as we saw here in New York, they're already creating these quantum networks. They're doing it in labs. They're starting to do it on a network-wide basis. Some of these things about encryption, they're not going to be able to do for a while, because in order to be able to do that encryption, you need to have a separate, you need to have a fiber optic connection to Amazon to do that today, because one of the things with quantum entanglement is it's a little bit sensitive, so that any kind of magnetic interference or other particles coming into contact with those entangled particles can mess up the entanglement. So everything's got to be very, very controlled. So they're trying to figure out all of those problems, both on the computing level as well as the network level. So it's going to be a while before we see this where you and I are using it, but they're already making some strides in using this in smaller areas, and even citywide, as we see here in some cases where they're doing testing and doing some applications citywide. But as you go out further, it gets harder and harder to do, again, because of just the fragility of this connection right now. But just like anything, we'll be seeing how this will be taking shape, and we'll see that I think within, again, 5 to 10 years, we'll be hearing more and more about quantum computing and quantum networking, and possibly at some point using it here. Again, not the too distant future. So I think it's very interesting. So thanks for joining me. If this was educational, if you give me just a like on the video. If you're not subscribed, click the subscribe button, click the bell to be notified when I'm live. I'll be live tomorrow with broadband deployment news at some point during the afternoon, and I will see you then. Bye-bye.